Good morning. Today we shall consider a famous experiment known as Young's double slit experiment. This is abbreviated as YDSE. This experiment was first demonstrated by Sir Thomas Young in order to explain the interference of light, and this is nothing but the experimental setup for the Young's double slit experiment. It is also called as Young's two-slit experiment because in this experiment the two slits are used, S1 and S2. These S1 and S2 are the monochromatic coherent sources of light. We will study these two terms, monochromatic and the coherent sources, in our next lecture. So here this is AB is nothing but the opaque screen, for example a cardboard paper, and in that cardboard paper the two slits are made, S1 and S2. L is nothing but the convex lens and S is the primary source of light. Okay, so these two sources S1 and S2 are obtained by this primary source of light. So these are the coherent secondary sources of light. For the time, you just understand that if the two sources are obtained from the same single source of light, then such two sources are called as coherent sources of light. Now, according to the Huygens principle, these two sources now become secondary sources of light and emits the secondary waves. And those secondary waves are shown by these dotted semicircles and the solid semicircle. So the apparatus used in the experiments are S, primary source of light, L, convex lens, A, B, opaque screen, S1, S2, two monochromatic coherent sources of light. Don't forget to write the monochromatic and coherent, these two words, in the examination. Here PQ is the screen. Okay, so a parallel plane wavefront is incident on the two slits S1 and S2 as shown in the diagram, and this plane wavefront is obtained by placing a source of light, point source of light, at the focus of the convex lens. So when a plane wavefront is incident on S1 and S2, these two now becomes secondary source of light and emits the secondary wavelets. Now when crust off, for example, if this dotted semicircle represents the crust of the first source and this dotted circle represents the crust of the second source S2, then when crust coincides with the crust of other wave, here the crust of one wave coincides with the crust of another wave, then here at this point of intersection the bright band is formed. We have seen in our last lecture, if the two interfering waves are in same phase, means when crust coincides with crust and trough coincides with trough, then there is a formation of maximum displacement, maximum amplitude and maximum intensity point, which is called as bright band, or it is called as constructive interference. So in the interference pattern, the central fringe is always bright, called as central bright band or central bright fringe. Okay. Now here, at these 2 points where crust of one wave coincides with the trough of other wave. This solid semicircle represents the trough. So here crust coincides with trough. Here also crust coincides with the trough. Therefore, there is a formation of the dark band, and these are the successive first dark bands. Okay. So on the screen which is placed in front of the two slits S1 and S2, here screen is PQ. So on the screen interference pattern is observed. Okay. So in interference pattern, at the center there is a central bright band, and the alternate dark and bright bands are spaced about this central bright band. Okay, this is the screen I have shown here. So at the center there is a central bright band. Note that in interference pattern, central band is always a bright band, which is called as CBB, central bright band. Okay, above the CBB there is a first dark band, then alternate first bright band, second dark band, second bright band, third dark band, and continues. Same below to the central bright band, the first dark band, first bright band, second dark band, second bright band, and third dark band. And this is nothing but the Young's double slit experiment. Young's double slit experiment मध्ये एक प्रायमरी सोर्स ऑफ लाईट आहे, आणि या प्रायमरी सोर्स ऑफ लाईट पासून आपण दोन सोर्सेस ऑफ लाईट मिळवतो. या दोन सोर्सेस ऑफ लाईटला बोललं जातं मोनोक्रोमॅटिक कोहरंट सोर्सेस ऑफ लाईट. ओके. ए बी ही ओपॅक स्क्रीन आहे, एक कार्डबोर्ड पेपर आहे ज्याच्यामध्ये हे दोन स्लिट्स तयार केलेले आहेत, आणि त्याच्या समोर या स्लिटच्या समोर बरोबर पुढे एक स्क्रीन प्लेस केलेला आहे PQ, ज्याच्यावरती आपल्याला इंटरफरन्स पॅटर्न मिळणार आहे. सो इनिशियली एक प्लेन वेव्हफ्रंट, आपण प्लेन वेव्हफ्रंट आपल्या सेकंड लेक्चरमध्ये स्टडी केलेला आहे. जेव्हा एखादा प्लेन वेव्हफ्रंट या S1 आणि S2 या दोन मोनोक्रोमॅटिक कोहरंट सोर्सेस ऑफ लाईट वरती इन्सिडेंट होतो, आणि हा जो प्लेन वेव्हफ्रंट आहे हा मिळवण्यासाठी आपण काय केलंय, एक पॉइंट सोर्स ऑफ लाईट बरोबर या कॉन्व्हेक्स लेन्सच्या फोकसवरती प्लेस केलेला आहे. सो जेव्हा हे रेज S पासून कॉन्व्हेक्स लेन्सवर पडतील, कॉन्व्हेक्स लेन्स मधून बाहेर आल्यानंतर ते काय होणार आहेत, प्लेन वेव्हफ्रंट पॅरलल टू ईच अदर. सो जेव्हा असा प्लेन वेव्हफ्रंट या दोन मोनोक्रोमॅटिक आणि कोहरंट सोर्सेस ऑफ लाईट वरती पडणार, त्यावेळेला S1 आणि S2 अकॉर्डिंग टू हायजीन्स प्रिन्सिपल सेकंडरी सोर्सेस ऑफ लाईट म्हणून बिहेव करणार आणि सेकंडरी वेव्हलेट्स इमिट होणार. इथे जे डॉटेड सर्कलनं दाखवलेलं आहे ते आहे क्रस्ट्स, आणि जे सॉलिड सेमी सर्कलनं दाखवलेलं आहे ते आहे ट्रफ. सो ज्या वेळेला क्रस्ट ऑफ वन वेव्ह हा दुसऱ्या वेव्ह सोर्सच्या क्रस्टवरती इन्सिडेंट होणार, तेव्हा आपल्याला मिळणार सेंट्रल ब्राईट बँड, आणि ज्या वेळेला क्रस्ट हा ट्रफ बरोबर ती कोइन्साइड होणार किंवा इंटरफिअर होणार, आपल्याला मिळणार फर्स्ट डार्क बँड. हे आपण आधीच्या लेक्चरमध्ये पाहिलेलं आहे, आणि या स्क्रीनवरती आपल्याला इंटरफरन्स पॅटर्न मिळणार आहे. इंटरफरन्स पॅटर्न हा अशा पद्धतीनं असतो, जिथे सेंट्रल ब्राईट बँड हा सेंटरमध्ये आहे आणि त्याच्या वर आणि खाली इक्वली स्पेस्ड डार्क आणि ब्राईट बँड्स अल्टरनेटली स्पेस्ड केलेले आहेत. हा आहे यंग्स डबल स्लिट experiment. Okay. Now, the second article is analytical treatment of interference. In analytical treatment, we are going to find the path difference between the two interfering waves. Okay. Same diagram we are using here. Just this part is removed. Okay. S1 and S2 means these two sources of light, coherent and monochromatic sources of light, and this small d is nothing but the distance between the two sources. Okay, here we are using small d as well as capital D, so you have to distinguish between these two carefully. small d is the distance between two coherent monochromatic sources of light, and capital D means the distance between the sources of light and the screen. So distance from here to the screen, it is shown by the symbol capital D. Okay. So for this experiment, this distance capital D is very much greater than that of the small d, and the second condition is that this distance d is comparable to the wavelength of the light. For our sake of convenience, here we shown these two distances in wider form or in macroscopic form. Actually, this d will be in terms of 0.5 mm, etc. Okay, mm means 10 raised to minus 3, means the term is like this. Okay, so this distance is very small. Okay, and here this small d is small as compared to the capital D. So this is the screen here, PQ, the screen. Okay, and this O is nothing but the central bright band, this. Okay, now we are going to decide whether the point P will be a bright point or a dark point. आपल्याला इंटरफरन्स पॅटर्न मध्ये माहिती आहे, जो सेंटरचा बँड आहे तो नेहमी ब्राइट बँड आहे, बिकॉज जर मी S1 पासून एक वेव्ह O पर्यंत काढली आणि S2 पासून एक वेव्ह मी O पर्यंत काढली, तर डायग्राम मध्ये आपल्याला दिसत आहे O is at the same distance from S1 and S2. Okay, because this QO is the perpendicular bisector of S1 and S2. So obviously S1O is equal to S2O. So when S1O is equal to S2O, then the path traveled by these two waves coming out from S1 and S2 to O will be same. So there is no any path difference. Means S1O आणि S2O या वेव्ह मध्ये पाथ डिफरन्स किती असेल, 0 असणार आहे. आणि आपण आपल्या मागील लेक्चर मध्ये पाहिलेला आहे, जर पाथ डिफरन्स हा 0 असेल दोन इंटरफरिंग वेव्स मधला, तर तिथे ब्राइट बँड फॉर्म होतो. म्हणून सेंटरला ऑलवेज कोणता बँड तयार होणार, ब्राइट बँड तयार होणार. आणि या अनालिटिकल ट्रीटमेंट मध्ये आपण एक पॉइंट अज्युम केलेला आहे स्क्रीनवरती, कोणताही पॉइंट आहे तो ब्राइट आहे का डार्क आहे हे आपल्याला स्टडी करायचं आहे. सो मला जर एखादा पॉइंट हा ब्राइट आहे का डार्क आहे हे जर मिळवायचं असेल, तर मला पाथ डिफरन्स फाइंड आउट करावा लागेल दोन इंटरफरिंग वेव्स मधला. सो आपण S1P जॉईन केलेला आहे आणि दिस S1P इज नथिंग बट द लाईट वेव्ह. Okay, arrowhead is shown, and this is S2P, which is the path traveled by the wave which is coming out from S2 reaching to the point P. आणि आपल्याला डायग्राम मध्ये क्लिअर कट दिसत आहे S1P हे डिस्टन्स S2P इतकं नाही. हे दोन्ही डिस्टन्सेस कसे आहेत, डिफरंट आहेत. S2P हे डिस्टन्स S1P पेक्षा जास्त आहे. सो मी जर S1 पासून S2 पर्यंत निघालेल्या वेव्ह पर्यंत एक परपॅन्डिक्युलर ड्रॉ केला, तर हे दोन डिस्टन्सेस सेम आहेत, इथून इथपर्यंत आणि या पॉइंट पासून या पॉइंट पर्यंत. सो द एक्स्ट्रा डिस्टन्स इज दिस. ओके, कॉल दिस डिस्टन्स or call this point as Z, suppose. Okay, so here S2Z is nothing but the extra path difference between these two interfering waves. Okay, so our aim is to find this S2Z, means the path difference, or in a straightforward language S2P minus S1P, म्हणजे या दोन पाथ्स मधला डिफरन्स. सो आपण शेवटी फाइंड आउट करणार आहोत S2P minus S1P, and this S2P minus S1P is nothing but the path difference. Okay, so mathematical part आहे स्ट्रेट फॉरवर्ड. त्यासाठी जर हे डिस्टन्स S1 आणि S2 मधील D असेल तर ऑब्व्हियसली OM आणि ON हे डिस्टन्स रिस्पेक्टिव्हली किती असतील? D/2 D/2. Small x is nothing but the distance of the considered point P from the central bright band O, small x. नेक्स्ट लेक्चर मध्ये आपण कॅपिटल X पण यूज करणार आहोत, पण हा X आणि कॅपिटल X हा डिफरंट आहे हे लक्षात घ्या. ओके, सो फ्रॉम ट्रायंगल S2NP means S2NP, this large triangle S2NP. From this large triangle, according to Pythagoras theorem, S2P square is equal to, means S2P square is equal to S2N square plus NP square. Okay, so what is the value of S2N? S2N is nothing but the small d, so here d square plus NP. We can write this NP as OP plus ON. Okay, so OP plus ON gives NP. So OP plus ON is equal to D square as it is plus OP means X and ON means D/2. Okay, square. So by using the expansion A plus B bracket square, we can write S2P square is equal to D square plus X square plus 2 into X into D/2 plus D square by 4. So S2P square is equal to D square plus X square, 2 get cancelled with one another, XD plus D square by 4. Okay, similarly from triangle S1P, S1MP. Okay, so S1M means this P, S1MP, again a right angle triangle, so apply Pythagoras theorem. S1P square is equal to S1M square plus MP square. Okay, again we can write this MP as OP minus OM. Okay, so OP minus OM bracket square, so it is equal to D square plus X minus D/2 bracket square, which is equal to, again use the same expansion and finally obtain D square plus X square minus XD plus D square by 4. So subtract equation 1 from equation 2. So S2P square minus S1P square, do these mathematical manipulation, and finally we'll get this A square minus B square means A minus B into A plus B. So we can write S2P square minus S1P square as S2P minus S1P into S2P plus S1P, and after solving this finally we'll get 2XD means XD minus minus plus XD, so XD plus XD which is equal to twice XD, आणि राहिलेल्या टर्म्स काय होतील? कॅन्सल होतील. ओके, नाव here X and D, this distance X and distance D. Okay, both these distances are very small as compared to the distance capital D. So we can write here S1P means this distance S1P is exactly equal to S2P because these two distances are very small. So here S1P equals to S2P which is equal to capital D. When this point P comes to the point O, assume then in that case S1P equals to S2P equals to D. So we can write S2P minus S1P, S2P as D, S1P as D, which is equal to twice XD. So S2P minus S1P is nothing but the path difference shown by the symbol delta X, which is equal to twice XD upon 2D here. Okay, so delta X equals to XD upon D, and this is nothing but the path difference, this extra distance S2Z. Okay, between the two interfering waves. आता जर हा path difference हा integer multiple of lambda आला तर P हा bright point, आणि जर हा path difference odd integer multiple of lambda by 2 असेल तर हा झाला dark point, आणि हे आपण उद्याच्या लेक्चर मध्ये पाहणार आहोत. थँक्यू.
Young's double-slit experiment. We have earlier discussed the phenomenon of interference of waves. Therefore, it is natural to expect that light also exhibits the phenomenon of interference. But interference of light is not so evident as the interference of sound waves. This is due to the very small wavelength of light waves as compared to the wavelength of sound waves. In 1801, Thomas Young demonstrated successfully the interference of light by performing a double-slit experiment. Young allowed sunlight to pass through a hole and then at some distance through two pinholes, S1 and S2, when light was received on a screen. An uneven distribution of light intensity was observed on the screen. A number of alternate dark and bright spots were seen on the screen. The phenomenon of interference can be understood on the basis of Huygens' principle. The secondary wavelets coming from S1 and S2 have equal amplitude, velocity, and wavelength. In figure, the continuous circular arcs represent the regions of wave crest. The dotted circular arcs represent regions of wave trough. At points marked by small circles, the trough of one wave is superposed over the trough of another wave, or the crest of one wave falls over the crest of another wave. According to the principle of superposition, the amplitude and hence the intensity of the resultant wave is maximum at these points. Similarly, the intensity is minimum at points marked by a cross. Thus, the resultant intensity is maximum along the lines connecting the crosses. On the screen, we get a number of alternate dark and bright regions of equal width. This is called interference pattern. Analytical treatment of interference. In the experimental setup, we use a sodium source of light. It gives an intensively bright golden yellow light. Ahead of this source of light, we have a single slit. It is rectangular and arranged vertically. It is nearly 1 mm wide, symmetrically to S. There are two slits, S1 and S2, which are nearly 0.3 mm wide. The distance D between the two slits is nearly 1 mm. A screen is held parallel to the slits at a distance of nearly 2 meters. The above arrangement ensures that light waves coming from S1 and S2 in the same phase. So, S1 and S2 are coherent sources. Let us consider a point P on the screen. When either S1 and S2 alone is open, there is a continuous full light all along the screen. However, when both the slits are open, this uniformity disappears. Instead, we have a set of alternate bright and dark vertical lines, equally thick and equally distant from each other. These are called interference fringes. In arriving at P, the waves from S1 and S2 have to travel different paths. So, the waves arrive at P with a certain path difference. If path difference is equal to n lambda, or phase difference is 2n pi, then the two wave trains reinforce each other, giving a fringe of high intensity. If path difference is equal to n plus 1 by 2 into lambda, or phase difference is n plus 1 by 2 into 2 lambda, that is 2n plus 1 pi, then there is destructive interference between the interfering wave trains and we get a dark fringe. Now, S1p square minus S2p square equals to d square plus y plus d by 2 whole square minus d square plus y minus d by 2 whole square equals to 2yd, or S2p minus S1p. S2p plus S1p equals to 2yd, or S2p minus S1p equals to 2yd plus S2p plus S1p equals to 2yd by 2d equals to yd by d. Therefore, S2p equals to S1p equals to d. For a bright fringe at P, yd by d equals to n lambda, where n equals to 0, 1, 2, 3, so on, or y equals to n lambda d by d, when n equals to 0, y naught equals to 0. The central fringe is bright when n equals to 1, y1 equals to lambda d by d, first bright fringe. When n equals to 2, y2 equals to 2 lambda capital D by small d, second bright fringe. Distance between two consecutive bright fringes equals to fringe width omega equals to yn plus 1 minus yn. Therefore, omega equals to n plus 1 into lambda capital D by d minus n lambda capital D by small d equals to lambda capital D by small d. For dark fringe at P, yd by capital D equals to n plus 1 by 2 into lambda, where n equals to 0, 1, 2, 3, so on, or y equals to 2n plus 1 into lambda capital D by 2d, when n equals to 0, y dash naught equals to lambda capital D by 2d. First dark fringe, when n equals to 1, y dash 1 equals to 3 lambda capital D by 2d. Second dark fringe, and so on. Distance between two consecutive dark fringes equals to fringe width. Omega equals to y dash n plus 1 minus y dash n equals to 2 into n plus 1 into lambda capital D by 2d minus 2n plus 1 into lambda capital D by 2d equals to lambda capital D by d. Thus, all fringes, whether bright or dark, are equal in width. To find the wavelength of light, lambda equals to omega d by capital D. Lambda is generally expressed in angstrom units. A. 1 angstrom equals to 10 to the power of minus 10 meter. Comparison of intensities of maxima and minima. If I1, I2 are the intensities at the observation point due to two separate sources of disturbance. Then I1 by I2 equals to A1 square by A2 square, where A1 and A2 are the corresponding wave amplitudes. However, in the case of interference, the amplitudes at maxima and minima are A1 plus A2 and A1 minus A2 respectively. I maxima, I minima at the intensities at maxima and minima respectively. Therefore, I maxima by I minima equals to A1 plus A2 whole square by A1 minus A2 whole square equals to A2 square, A1 by A2 plus 1 whole square by A2 square, A1 by A2 minus 1 whole square equals to A1 by A2 plus 1 whole square by A1 by A2 minus 1 whole square. Put A1 by A2 equals to R, amplitude ratio. Then I maximum by I minimum equals to R plus 1 by R minus 1 whole square.